Hi, everyone. I'm Johannes. So today I would like to talk about a new approach to learn multi-item auctions that allows us to go beyond the standard item independence assumption. This is joint work with my student Johannes Brustle from McGill and also Constantinos Daskalakis from MIT. Okay, so the problem we're interested in is you want to say settle an auction to maximize the revenue. So here's a very simple setting. So usually the values of the bidders are private to them. So if the seller does not know anything about these values, this is not even a well-defined problem. So usually you would need to make the following assumption. Namely, you assume these values are drawn from a distribution F, and the seller knows this distribution F. Okay, so this is known as the Bayesian assumption, and it plays a key role towards an analytic solution to the problem. And indeed, Meyerson shows that under this assumption, there's a very simple characterization of the optimal mechanism if the bidder's values are independent. So if you really think about this assumption, you may ask, where exactly did the priors come from? So the common answer is these priors come from market research or maybe observation of bidder behavior in selling the same type of item in some prior auctions. But if this is the case, maybe you don't really know the distribution F. A reasonable assumption would be maybe you know you have sample access to this distribution. And this is what I call the sample-based mechanism design. And the goal here is, given sample access to distribution F, learn an approximately optimal or up to epsilon optimal auctions. And here by approximately optimal, I mean you can get a multiplicative approximation to the optimal revenue. And up to epsilon means you have an additive epsilon error. In the single item setting, where Meyerson's characterization applies, we understand the problem very well. We have almost matching upper and lower bounds on the sample complexity to get 1 minus epsilon of the optimal revenue. And how about for multi-item auctions, which is the setting we care about? So here, due to the lack of general characterization, results are sparser, but there are still some interesting positive results known. All under an extra assumption called item independence, which means every bidder in this auction will have independent values across the items. Okay, so the results here, most of them are obtained using a pack learning-based approach. I will say more about this approach in the next slide. There is one exception by Goldner and Carlin. The result is directly sample-based, but tailored to a specific mechanism. And all results here, except the one by Gonzalowski and Weinberg, gets a constant factor approximation to the optimum revenue, and their mechanisms are dominant strategy and incentive compatible. The one by Gonzalowski and Weinberg actually gets an up to epsilon optimal mechanism, but the mechanism is only approximately Bayesian incentive compatible. Okay, so what are the three goals of this paper? So the first thing I want to talk about is, the first goal is that we want to extend the result by Gonzalowski and Weinberg to handle dependent items. The second goal is that we want to provide a modular approach that decouples the inference and mechanism design components in the previous approaches. Okay, so what do I mean by that? So if you apply a pack learning approach, that requires you to find a fine balance between two properties. So the first property is you want to identify a rich enough class of mechanisms that is guaranteed to have an approximately optimal one for the class of distributions you care. Okay, to do that, you will need to understand mechanism design quite well. The second property is that the class of mechanisms should not be too rich, in the sense that you can learn with only a small number of samples. And this is usually characterized by having a small enough statistical complexity. For example, the VC dimension, pseudo dimension, or Rademacher complexity. And to this step, you will need to have a good understanding of learning theory. The tricky thing here is these two properties are at odds with each other, and you will need to consider them together to get the right trade-off. And the approach I'm going to present today actually avoids joint consideration of these two properties. Okay, and the last goal of this paper is that I want to go beyond sample access. In fact, I don't want to assume that we can draw samples from the distribution. I only want to assume that we have access to an approximate distribution. Okay, we call this robustness. So in the next few minutes, I will show you how to achieve these three goals and how they're related to each other. And I would like to start with robustness. Okay, so when is having sample access a reasonable assumption? Well, it's a reasonable assumption when you can observe bids in previously run truthful auctions. But very often, you only have access to bids in non-truthful auctions. And the common practice here is you apply some econometric methods to invert the bid distribution to uncover a value distribution. But after doing that, you still don't have sample access to the value distribution. Most likely, you will have an approximate version of the value distribution. And that's the motivation for our robustness model. So in our model, we assume that for every bidder, we're given an approximate distribution, Fi hat. The true world, where everyone's distribution is Fi, is unknown to us, but we know that the true distribution and the one they're given to us is within epsilon in some statistical distance. And the goal here is you want to find a mechanism M such that for any possible true world, the mechanism M that you designed using only information about F hat has revenue that's almost as good as the optimal mechanism just designed for the true distribution. Okay, so that's our goal. And a priori, it's not even clear if such a mechanism exists, because you need to design a single mechanism that achieves almost optimal performance with respect to everything in the epsilon ball. Okay, so in this paper, what we showed is such a mechanism does exist if you allow approximate Bayesian incentive compatibility. And one nice feature about this result is that it allows arbitrary dependency between the items. So we're not making any item independence assumption here. We studied this robustness model under several statistical distances. The one I find most interesting is the Prokhorov distance. So let me say a few words about the Prokhorov distance. It is widely used in robust statistical decision theory. And let me give you an intuitive understanding or the meaning why when I say two distributions are close under Prokhorov distance, what it means. Okay, so if Fi hat and Fi are close in Prokhorov distance, that means only the following two types of error could happen. One is with large probability, maybe the value has been misperceived by a small margin, or with a small probability, the value has been misperceived by a large margin. Okay, these are the only two types of errors that could happen. And I also want to point out that the Prokhorov distance is a very liberal distance. If you can prove robustness for the Prokhorov distance, it automatically implies robustness for a lot of familiar distances, such as Weierstrass distance, TV distance, Hellinger, and chi-square distance. And what do we know about robust mechanisms? The result by Bergman and Schlag considers a very similar model, but only for one bidder and one item. And they also use the Prokhorov metric, and they characterize the exact max-min optimal mechanism. There's an earlier paper by Costas and myself. There we assume the items are independent, and we only constructed a mechanism that's robust, but gives you a constant factor approximation. So in this paper, we remove the independence assumption, and also we can get a robust mechanism that gets almost optimal revenue. And here's a summary of our robustness result. I won't go over the table very carefully. So for single item setting, we consider the Kolmogorov distance and the Levy distance. For multi-item setting, we consider the TV distance and the Prokhorov distance. One thing I want to point out is that in the single item setting, we can actually design a mechanism that's exactly dominant strategy incentive compatible. While in the multi-item setting, we have to settle for approximate Bayesian incentive compatibility. Another thing I want to mention is there is an interesting byproduct of our robustness result, namely the continuity of the optimal revenue. So we also show that under these different distances, the optimal revenue is continuous. Okay, so that's the robustness result. Now let me tell you the modular approach. And the meta theorem that we prove in this paper is that if you have the robustness result, now all you need to do is be able to learn the value distribution within some statistical distance epsilon. Okay, once you have that, you can put these two things together and you obtain a sample complexity. And what I want to point out is the robustness mechanism design, actually you don't need to understand anything about learning theory. And for learning distributions, there's nothing about mechanisms. And an easy corollary of this meta theorem allows us to recover the results by Gontarowski and Weinberg because they consider the case where the value distribution is a product measure, and learning product measure within Prokhorov distance epsilon is rather straightforward. Okay, so now let me talk about how to learn auctions with dependent items. So the first thing I want to discuss is how do we actually model dependence? So if you allow arbitrary dependence, that's not going to work because it requires exponential samples. In fact, Dukmi et al. Showed that if you allow the items to be arbitrarily dependent, you will need exponentially many samples to just get a constant vector approximation for a single bidder. And in fact, the instance in Dukmi's paper requires very strong dependence. So what we want to do in this paper is to come up with first a model that captures the degree of dependence in the distribution, then provide parameterized sample complexity that degrades gracefully with this degree. And of course, capturing dependency in high dimensional distribution has been studied by the machine learning and statistics community for quite some time. So what we do is we take two of the most prominent models to capture the dependency, namely the Bayesian networks and Markov random fields. In the next slide, I will show you two examples about these two models. But first, let me say that these two models are fully general. If you allow the graphs that these models are represented on are sufficiently dense. So you can use both models to capture arbitrary dependence. And what is the parameter in these models to capture degree of dependence? Well, in MRF, the dependence degree is captured by the maximum size of hyperedges, while in a BaseNet, that's captured by the largest in degree. And our result also allows you to have latent variables in these models. So these are models, so these are variables that are unobservable from your data. Okay, so let me give you two examples. So BaseNet is a model that you can represent as a directed acyclic graph. And the nodes in the graph are the random variables. So here I have a very simple BaseNet. So at the root, that's a latent variable, which represents, say, the state of residence of the buyer. Condition on that, the buyer's value for the four items I listed here will be independent. Okay, so that's a particular dependency. But if you don't condition on the state of residence, say you just condition the values of two of these items, say, skis and surfboards, but then the buyer's value for umbrella and sunglasses will still be correlated. Okay, so this is one example of BaseNet. In MRF, the model is represented by an undirected graph. And now you can have cycles. And again, the nodes are the variables. If there's an edge between them, that means these two variables are dependent. Okay, so these are the two models we considered. And we obtain new sample complexity for learning both BaseNets and MRFs within Prokhorov distance epsilon. I don't want you to look at these polynomials too carefully, but what I want to point out is our bounds, the sample complexity, has polynomial dependence on all the parameters of the model, except the degree of dependency. For that, we have exponential dependence, but that's unavoidable. And also, our result generalizes a recent result by De Vroy et al. That only considers special cases of MRF. Now, if you plug in these sample complexity for just learning MRFs and BaseNets with our robustness result, you can obtain sample complexity for learning up to epsilon optimal eta big mechanisms. And again, I want to point out the exponential dependence on this degree D is unavoidable, just due to the dopamine result. Okay, so let me quickly show you some proof vignettes, and I want to talk about the maximum robustness. So just to remind you, in the maximum robustness, you're given just one distribution f hat, which is the center here. And you want to design one mechanism M that works for every distribution that's around the epsilon ball here. Okay. And what I want to convince you is you can actually prove that the Prokhorov robustness is equivalent to the TV robustness. And the TV robustness is rather easy to establish. So that will also give you the Prokhorov robustness. One direction is actually quite easy. The reason Prokhorov robustness implies TV robustness is just because the epsilon Prokhorov ball contains the epsilon TV ball. Okay. But the other direction is a bit tricky. One may hope to just enlarge the TV ball to contain the epsilon Prokhorov ball. But turns out, even if you enlarge the TV ball to have radius 1 minus delta for arbitrarily small delta, that still does not contain the epsilon Prokhorov ball. Okay, so you have to do something else. What we did, so I won't have time to go into details, but let me just tell you the key idea that we use to prove the reduction from Prokhorov robustness to TV robustness. That is, you don't consider the original distributions. You should round these distributions down, okay? But you round them down to a random grid, okay? So why is that a good idea? So here I have a blue distribution and a red distribution. And first, let me tell you the Strasson's characterization of the Prokhorov distance. So if these two distributions are close in Prokhorov distance, that means you can have a coupling such that the two couple points have distance more than epsilon. That happens with probability less than epsilon. Okay, so let me show you the coupling. So the 2 points are coupled together using a green line if their distance is less than epsilon. They're joined by an orange line if their distance is more than epsilon. Okay, and then what I would do is I will draw a uniform point from this green square, which has width root epsilon. Okay, and I will use this randomly draw point as the origin of my grid. And my grid also has width root epsilon. Okay, now what I do is I round the blue points and the red points to the bottom left corner of the square they're in. Okay, so what I can show is if you consider two rounded distributions and their TV distance between these two rounded distributions, that's a random variable because that depends on the origin. But the expected value of this TV distance is quite small. It's only root epsilon. And the reason that this is indeed a case is not hard to see. Because if 2 points are actually far away from each other, okay, there's basically no hope for them to actually end up in the same point in the rounded distribution. But since 2 points are far away from each other, only with probability epsilon, so that's fine. If 2 points are actually close to each other, say their distance no more than epsilon to begin with, sometimes they still might be separated by the grid. But that should happen not with very large probability because their distance is epsilon, but the width of the square is actually root epsilon. So you have to be very unlucky to actually separate these 2 points. And in fact, you can argue that happens with probably root epsilon. And that's roughly the reason why we can prove this expected TV distance at most root epsilon. Okay, with that, you can apply the TV robustness to this rounded distributions and you get the proper robustness result. Okay, that's all. Thank you.